I hope all of you are doing good. I am Mr. Ish. Thank you for joining me for this video. In this video and the next two, a total of at least 3 videos, I want to present all of you something very interesting, a new way of thinking about your integrals using this theme of area between curves as our application for those 3 videos. In this video, we're looking at everything in a very simple manner using simple examples. Then in the remaining 2 videos, we will increase the complexity of those examples. If I gave you this representation over here, A and B, C and D are horizontal and vertical limits. You know imaginary lines can go through these limits, but I've delimited everything here by means of segments, and you see that. This here would be a lower boundary curve. You know it would be y is equal to c because it would go through c. This here would be an upper boundary curve, which would be y equals d because it goes through d. You know that. You have vertical lines here. There's a vertical line going here through A, and that would be x equals A. There's another vertical line here going through B, and that's x equals B. If I told you the region between here, these lines, these equations, you can present them in 2 ways. Area with regards to x, you can look at everything with regards to the x-axis integral, and you would have A to B horizontal limits, top boundary curve minus lower boundary curve dx, and you know top boundary curve would be d, lower boundary curve would be c. Those would be your 2 functions you'd integrate. The other way you can do this, area with respect to y, you would look at everything now with regards to your y-axis or vertical line of axis c to d. You'll have a right boundary curve minus left boundary curve dy, and you know all of this. Your right boundary curve would be this vertical line x equals b, your left would be x equals a, and it's easy. But look, in each of these particular instances you have a primary variable. Here your variable is x, here it's y. You have a single integral and a single limit interval that you're worrying about. That's it. I will show you a different way of doing all of this using this as an example, and we will be required to now broaden our horizons and start thinking in a new way with regards to integrals. This new way, you can essentially say it as you are integrating a limit. You know what a limit is, a limit interval over a limit. That's what we're doing. Or you can say we're integrating an interval over an interval. You can even say we'll be integrating a definite integral over a definite integral. But in all of these instances, by means of these limits, you end up seeing segments. If you have a particular line which goes from minus infinity to infinity, you can always break it down into a segment by throwing in limits. That's exactly what we end up seeing, segments. We're integrating segments, we're not integrating lines, the area between segments, the area below segments, all of that. What is this new way? Well, as I have alluded to you, integrating a limit over a limit, or integrating an interval over an interval. And I also said integrating a definite integral over a definite integral. Hence, the double integral comes into play. Start in the following way. I have a line that I've now reduced to a segment by means of interval a and b. You know this right here is a segment. I have another set of limits going from c up to d. If I were to imagine taking this interval and move the interval up, I will generate a new over here. Between the old, between the new, I can now generate a quadrilateral for which an area can be determined. How can you show all of this by means of an integral? Look right here at your horizontal limits. If you put those into a limit, you're looking at a to b, lower limit to upper limit with regards to dx. Now, after we've established this, you don't even have to worry with regards to these parallel sided polygons or parallel sided areas generated between curves. You don't even have to worry about functions, because you know this right here is y equals c, this here is y equals d, x equals a, x equals b. You don't even have to worry about that. I've generated a interval represented by means of this integral. Now I'm going to integrate this integral over this limit, and look what I'll do. From c to d with respect to dy, and there it is. That's my double integral, where I'm integrating a limit or an interval or a definite integral over another limit, interval, and definite integral. When you integrate this, there's a hidden integrand from which you will get an antiderivative x from b to a. You'll do your computation, you'll have a b minus a. This b minus a will now come as a constant or a coefficient of your next integral. You will have b minus a coming before this integral c to d dy. There's no need for you to start establishing functions here. You don't need to. This works. B minus a times the antiderivative coming from here, d to c, the upper limit, lower limit, the difference of the two, you'll have b minus a times d minus c. B minus a will end up giving you a certain dimension. We'll call that length. D minus C will give you another dimension. We can call that length or width based on if you are having a square or a rectangle, and that's what you'll have, length times width, and you've generated an area of this quadrilateral by means of a double integral procedure. I could have put legitimate values here, 2, 4, 2, 4, and you would have gotten an area equals to 4. You can do this by your traditional procedure, the one I was showing you at the very beginning, yt minus yb integral dx, horizontal limits, or right and left boundary, vertical limits, and integral dy. Your end result will be the same. This here is a very legitimate way of looking at area between curves. Look at this representation. I have a vertical line which I'm breaking down into a segment by means of limits C and D. You see that? I want to move this in my head. I want to imagine I'm moving it across and re-establishing it here from an A to a B. By moving the segment over here, I'm generating here a quadrilateral for which an area can be determined. More simply, you can say I'm looking here at an interval or a limit, an integral which I will look across or integrate across another interval, limits or integral, and this is how we will look at it. Our initial integral will be this from C to D with respect to dy. This here represents what I want to integrate over something else, which is A to B with regards to dx, and that right here is my double integral, which will give you your area of this. From here you're getting your hidden integrand, which will give you your antiderivative D to C, and you know you'll get D minus C, which will now become the coefficient of that, or the constant applied to that, and you have A to B with regards to dx. From here you get your x, b, and a. You have this D minus C, and then you end up seeing D minus C times B minus A, your one dimension times another dimension, which will give you your area. And this is a perfectly legitimate way of you looking at area between curves. Just keep in mind, in this video I'm looking at parallel sided polygons. Everything is parallel. If I'm taking an interval between two limits and I'm moving it up, it's not diverging or converging because everything is parallel. If I'm taking a interval along the y-axis, then I'm moving it horizontally. Again, that interval limits are not expanding or contracting because there is no convergence or divergence. Everything is parallel. This here is parallel to that here is parallel to this side. So everything here I'm showing you in this video is parallel sided, which is why this is easy. In the other two videos I'll show you procedures which are involved when you don't have parallel sides. Here simply moving an integral limit across or over is easy. Everything is parallel. Your essential take-home message is this: you're starting out with an integral which is part of a region between curves, but everything is parallel sided. You're treating this as a kind of a function which will then integrate over something else. It could either be the other way, dy and then dx, or dx and dy, but you are essentially integrating an interval or a limit over another interval or a limit, and a definite integral procedure gets thrown into another definite integral procedure, and you end up with double integrals. That's it for this video. I'm showing you everything here in a conceptual manner, but everything I'm showing you here is good. Thank you for watching. Have a good day.